Hello everyone, this tutorial is going to provide you some hints on the last assignment, number 10. So we'll start with problem 1. The problem 1 is a fairly standard procedure on evaluating surface integral. So we have three different questions. First, number 1 step is you have to identify what kind of surface do you have. Basically, you need to set up the surface integral using different coordinate system. So the first one here, the acid surface is sphere with the radius of 3 basically, and the direction is given is outward. So chances are here you probably will want to use the spherical coordinates. Okay. So if you want to use spherical coordinates, then we have to set it up according to that surface integral. And the n hat, because it's a spherical coordinate, so n hat will be 1 over the radius and x, y, z. Okay. The dA, okay, you set it up according to d phi and d theta, and fill out the blank here, okay, which is a squared sine phi. Okay, so r9 is the radius to the power there, so 9. Okay, so of course there's rx equal to sine 3 phi, cosine theta, y equal to 3 sine phi, okay, and sine theta z equal to 3 cosine phi. So this is basically set up there. Okay, and the rest of the work is essentially just fill in the blank for the surface integral. Okay, f hat dot n hat dA over s. So dA you have it here. Okay, dA n hat you have it here. F is given. Okay, and this should be this. Okay, right. So now you can fill in all the blank and do the surface integral. Okay, find out the limits for phi and theta properly, okay, and you should be able to find. You should be fine for the part A, and of course, anyway, the phi range will be between 0 to pi, okay, and the theta range will be between 0 and 2 pi. Okay. And part B here is your vector fields, and as a rectangular surface. The rectangular surface here is y equal to 0, okay, and the range for x and z are given. Direction is also given, negative g. Okay, so this is a little bit different surface as I gave in the class. Okay, so given the class is the surface z equal to a, but here is y equal to 0. So in this case here, to set up the surface integral properly, okay, so what you're gonna have here is basically y equal to 0. And n hat is negative g hat, okay, and dA will be dx dz. So that's basically what you need to fill out the blank, right? Okay. Again, you have the dA over here, n hat over here, and f is given by the function. Okay, is given by the equation. Okay, so it should be fine in terms of finding this surface integral. Just fill out the blank. Okay, there. Okay, so that's basically what you're gonna have for this guy. Okay. Part C is also fairly standard. Okay. Now let's go back to part C here. Vector field is given here as the surface of the paraboloid as z equal to x squared plus y squared between z equal to 0 and y. So this is a paraboloid here. Now this is actually also in the format of this. So z equal to f of x, y. Now, so you do have this, okay. So essentially, this is what we call the explicit surface. Okay, and we match the case number 4 basically for the surface integral. Okay, in this case here, we're going to set up basically according to that type of surface. Okay. So z equal to this, okay, and n hat dA, okay, as we derived in the class, okay, is negative fx, negative fy1, and dx dy. Now I'm taking here as a positive here. I didn't take the negative. The reason is because the question says the direction is up at 0.000. Okay, so that's why we're taking n as n hat as up over there. Okay, and you have to, if you calculate the n hat and you plug in the 0, you want if you want n hat to be up, this sign here has to be positive here. Okay, yeah. So apparently, according to this question, it's going to be negative 1 dx dy. Okay, yeah. So set up this properly, okay, and plug in everything. Okay, so your surface integral, and your surface integral will be will turn out to be s negative ax squared minus ay squared plus 2 dx dy. Okay. Now, when we looking for the range for x and y, this is basically the xy range. Okay. Is determined by the shadow of the surface in the xy plane. Okay. The shadow of the s in the xy plane turn out to be, because it's a parabola, right? Because it turned out to be just a circle. The radius of the circle is determined by the range. Basically, the range says between 0 and 1, right? Okay, so the circle is x squared. So the shadow is a circle, x squared plus y squared equal to 1. Okay, so over here, to do this double integral, we'll use polar coordinates. Okay. So you will be able to transform this into in terms of r and theta. Okay. So because the shadow is x squared plus y squared equal to 1, that's the shadow. Okay. So the range for theta is 0 to 2 pi. The range for r is between 0 and 1. And substitute x, y properly. Okay. There. So that's what you're gonna get. That's what you're gonna get. Okay. Yeah. So this is basically how you're gonna do for problem number 1. Very standard forward. Problem 2. Okay. Needs a little bit attention. Okay, and careful in terms of solving this question. So what we have here, S is part of the spherical surface, this is the spherical surface, lying in x squared plus y squared greater than 1. Okay, which is to say outside the cylinder of the radius 1. Basically, x squared plus y squared greater than 1 is outside this cylinder. This is a cylinder. X squared plus y squared, that's a cylinder, right? And greater than 1 means any region outside this cylinder. So you have the sphere here, and it says it's a part of a line outside the cylinder. That's why you're looking at only this portion here. So you can imagine that this is like an apple. You take out the core of the apple, okay, and what's left is the surface we're looking at here. The vector field is given over here, and compute the flux outward through S. So direction is also given outward S. So here is your S. Okay, this is your S here. Okay, yeah. Okay, so part A is a standard application of surface integral. Okay, in this case here, because the surface is part of the sphere, so you want to use the spherical coordinates, and the n hat you will take as basically x, y, z. Okay, because the radius of the sphere is 2. Okay, 1 over 8. And dA is 4 sine phi, okay, and d phi and d theta. There. Then use properly the spherical coordinates, okay, and putting this n hat and dA, okay, for the S. So everything should be good. The only attention I need to remind you guys here is, after you get the surface integral, you get something like this. Okay. There. So you need to find out the range for phi and theta. So the phi and theta here, remember the way that we do in the spherical coordinates, we draw a reading lines out of the starting origin. Okay, so across the whole region, across basically where your surface is. Now, the phi is defined as an angle between z-axis and your reading line here. This is your phi. So apparently, your minimum phi angle is determined by the point between here and here, and the maximum phi angle is determined by the point between here and here. Okay, so what is this point over here? Now, because what we said here is this radius here is 1. Okay, this radius here is 1 because that's x squared plus y squared equal to 1. Okay, and the radius of the sphere is 2, so the phi angle here apparently is pi over 6. Okay, and that's the minimum phi, and the maximum is from here to here, so that'll be basically pi minus pi over 6, which you have 5 pi over 6 for this guy here. So then your phi angle is pi over 6 to 5 pi over 6. Okay, and theta angle is determined by you draw a reading line across this the shadow, which is the surface of the shadow in the xy axis, which is basically this guy here. Okay, and going around by 0 to 2 pi, that's your region. That's the limits for the theta. Okay, so now when you calculate this integral here, okay, what you need to really be careful, okay, is the following here. Okay, now there's nothing theta here, so I guess I can just move the theta here. Okay, so this guy here, what you need to do is very simple substitution rule. Okay, so d cosine phi, okay, there's a negative here, so let's put a negative here. There, right? And this integral, okay, is 1 over 3, okay, and negative, okay, and cosine phi cube, okay, and phi changing from here to here. Okay, so cosine pi over 6 is square root of 3 over 2. Cosine phi pi over 6 is negative square root of 3 over 2. Okay, so this guy here, so let's take this as 2 pi, okay, and negative 1 over 3, so negative square root of 3 over 2 cube, okay, minus square root of 3 over 2 cube here. Okay, then this guy here, okay, what's this guy here? That's 8 at bottom. The top over here is 3 square root of 3. Negative. Negative, same thing. Okay, like that. Okay, so you see negative and negative cancelled, 3 cancelled, and this is 16 pi, okay, and so we'll have a square root of 3 over 4, right, which you end up with 4 pi square root of 3. There, so that's the answer what you get. Okay, so part B show that the flux of this vector field through any part of cylindrical surface is 0. Okay, now we're talking about the surface of the cylindrical, which is the inside here. Okay, now not the surface of the sphere, but we're talking about the flux through the cylindrical surface, basically only the vertical cylindrical surface. You can do the similar thing there. Okay, okay, so part B. So what is the unit vector, okay, for the cylindrical surface over there? Okay, the unit vector for cylindrical surface is, according to what we learned in the class, is 1 over 2 x, y, 0. Okay, so let me see, what's the cylinder here? Cylinder is x squared plus y squared greater than 1. Okay, and this actually should be 1 here. Okay, because the radius of the cylinder is 1. Yeah. Now what you're gonna find out here is, for this unit vector, for this unit vector, and based on the vector field given here, the dot product between these two guys, okay, is gonna be 0. Okay, if this dot product is 0, then the surface integral, right? The surface integral and across this whole cylindrical surface is going to be 0. So that's why the part B here is very simple to show that the 0 flux there. Okay. Part C. Part C, it says use the divergence theorem applied to the vector field. Compute the volume of the region between S and the cylinder. So you have what's the volume of the remainder apple, right? If the apple is being eaten by a worm, right through this apple here, and then what's the remainder volume of the apple, basically. Okay, so let's take a look at the concept here using divergence theorem applied to it. Now, of course, we're going to learn that in the two selector. Okay, so but anyway, I'm going to put it here. So let's see here. Okay, first of all, divergence theorem. Okay, let's lay down the divergence theorem. Says here, divergence theorem says the surface integral for a closed surface, okay, is basically the closed surface will be able to transform into a triple integral over the region enclosed by the enclosed surface, closed surface. So here, what's my closed surface? The closed surface is composed of the spherical surface, right? Basically, composed of the sphere surface, the spherical, okay, or the sphere, and plus the cylinder. Right, so that's the surface, right? As you can see here, so the region, right, the solid, okay, is enclosed by this guy here and this cylindrical surface. Okay, so the surface integral is n hat dA. Okay, now we can transform this into this using a divergence theorem, div f vector, okay, and dv. Okay, yeah, so that's basically the surface integral, the divergence theorem. And let's expand it. Okay, let's expand this term here. So that's when you have two surfaces add together, so you're gonna have here is one is a sphere, okay, and one is cylinder, okay, cylindrical surface. Okay. So cylindrical, what's the flux across the cylindrical surface? Well, we did that. In part B, this portion here is 0, right? This portion here is 0. Okay. Now, what is the flux across this sphere? And we have also calculated that, okay, in the part A, okay, which is 4 square root 3 and pi. Okay. Well, we don't see the volume yet, right? We don't see any volume yet. But let's try to calculate this divergence F here. Let's see what does that give us. Okay. So divergence F, okay, is essentially just del dot F. Okay, del dot F. And if you do that, okay, and F is y negative xz. Okay. You actually will see it's 1. Okay, so the divergence, this term here, okay, this term over here, turned out to be the volume. This term here, they turned out to be the volume of this region enclosed by the sphere and the cylinder. Right, there's only one now, and that is the volume. Okay, what's the volume? volume equal to only 4 square root 3 of pi, right? Given by the flux going through the sphere. So that's what it means here in this question, using the divergence theorem to calculate the volume of this. Okay. Of course, you know, divergence here is not always 1, but it's just in this particular question. And this guy here is 1, so you can make use of this fact to calculate the volume. Okay. Problem number 3. Okay, problem number 3 here. Let S be the surface formed by the part of parabola. So you have parabola here, okay, and lying about the xy plane. So the only part, this part of the surface here. Okay, the vector field. Giving this, calculate the flux across this F. Okay, using 2 different methods. Okay, one way is to use direct calculation, and the second one to use divergence theorem. Okay. So let's take a look at part A here. This part A is very straightforward, using direct calculation. So what you do here, you already have an explicit surface, okay, which is this. Okay. You have an explicit surface here. Okay, and the question asks is taking upward direction. So you consider n hat as upward direction. So then what we do is we take this one as our direction here. Okay, n hat d n hat. This is actually the n hat dA is taken as this one here. Okay, okay. dx dy. Okay, and the rest work is basically plugging n hat dA, plugging the surface integral formula. Okay, okay, and start to do this surface integral. And it's very similar procedure in part 1C problem. Okay, so you'll be able to do that. Just remember, in this part you need to convert your Cartesian coordinates into polar coordinates when you are going to find the limits for x, y. Okay. So for part B, okay, use divergence theorem. Okay, now divergence theorem again, you know. You might say, oh well, how come divergence theorem give me a surface integral? But we're not talking about an enclosed surface here, right? You only talk about surface into the flux going over this surface here. But divergence theorem is a theorem applied to enclosed surface. Okay, so you have to consider some sort of region here. So what can give me an enclosed surface? Okay, so we look at this surface here and this bottom surface over here, which is basically the shadow of the surface in the xy plane. Now you consider these 2 surfaces. Now that will give me an enclosed area, okay, enclosed region basically by the 2 surfaces over here. One is its bottom here, and the other one is the top over here, right? Okay. So let's consider this enclosed region over here. So then what we have here is, okay, let's consider basically lay down this one here. Divergence theorem, okay, is this, okay, divf, okay, and dv, okay, right, will equals to the surface integral over this paraboloid, okay, which you calculate in part A, okay, and also plus the flux, okay, of surface integral of the bottom one, okay, the bottom one here. Okay, let's use a t as this surface here, the bottom here. Okay, yeah. Okay, so in this case here, you calculate this. Now, sorry, this one is what I want to know, right? So in this case here, then I can use, if I use divergence theorem, I said this surface integral, okay, which is for this paraboloid, will be the divergence, right, basically left side, okay, minus this integral, surface integral on the bottom here. Okay, yeah. So let's try to calculate these 2 terms to obtain the surface integral, which should be exactly the same as you obtained in part B. Okay, and you can examine which one is easier. Okay. Now let's see what is the surface integral for the unit disk at the bottom here. Okay, yeah. Now back to this question here. Okay, we're talking about the now you need to look at what direction for this surface, bottom surface. The direction can be this direction or it can be this direction here, right? Now to say the the flux right here, okay, for divergence theorem, okay, and always remember for the divergence theorem, the direction for the surface enclosing the region, you're always taking the outward direction basically, okay. So our direction means this direction and this direction. So you should not take this direction when you calculate the surface in the bottom here. You should take this direction over here, okay, this direction. So because it's a unit disk in the xy plane, then the unit normal direction for the unit disk over here, right, for this guy here will be n hat, okay, will be basically negative k hat, okay, negative k hat. Okay. So the surface integral for this bottom one here, okay, the t, okay, f n hat dA, okay, let's do that, will be x, y. Now let's go back to here. What's the f vector here? Right? F vector is x, y, this. Now, but when you're talking about a surface in the xy plane, then when the vector field across that surface in xy plane, that means the z value is 0. Okay, so the f right here is just 2. Okay, it's just 2 here. Okay. And n hat is 0, 0, negative 1. Okay, and dA, dA basically dx, dy. Okay, yeah, because it's a part of plane in xy there. Then you calculate this one here, you get negative 2 dA, right? Well, you can take the negative 2 out. Okay, so what you got over here, and this part here, that's basically the area of the unit circle, right? Unit circle. So the area of the unit circle is negative, okay, 2 pi r squared, and r is 1, so negative 2 pi. Okay, so that's basically the surface, the flux going across the bottom surface there. Okay. Now, what is the divergence over here? What's divergence? So let's try this guy here, right? Now, divergence, if you tried it out, you actually will see that this guy, for our particular case, okay, is actually gonna be 0. Okay, you can try it out. But for this vector field, the divergence is 0. Okay, so in this case, it's 0. So if this is 0, then it's pretty apparent. Then the flux across the paraboloid is equal to negative, okay, the flux across the bottom unit circle, and which we will have here 2 pi. Okay, so that's basically how you make use of this divergence flexibility and to obtain a surface integral. Problem number 4. Okay, so this is Stokes theorem, which I will cover that on the Tuesday lecture. Okay, and this is actually not too bad. Okay, so first for the Stokes theorem, okay, is relating a line integral with a double integral, a surface integral. Okay, so the surface integral here is this. Okay. Use Stokes to find the work done by vector field of this around the curve C, in which the plane z equal to 2 meets the cone z equal to this. So this is a part of the circle when the plane z equal to 2 meets that. Okay, so essentially when you plug the 2 over here, then this circle here, you project that, it'll be x squared plus y squared equal to 4. Okay, yeah. The curve is counterclockwise as viewed from above. The curve is counterclockwise viewed from above. Okay. Now this is important because in the Stokes theorem, you need to orient your surface, okay, which is bounded by the curve C, okay, properly according to the direction of the curve C. Okay. Now because the curve C here is going counterclockwise, then using the right-hand rule, okay, your your surface over here, for basically is the part of the cone, needs to be oriented using n hat, using right hand rule, which will be this direction over here. Essentially, it's up direction. Okay, it's up direction. Okay. So use the right hand rule and use the direction of the curve C to properly orient your surface, which is bounded by the curve C. Okay. Yeah. Okay. So the curve C, now you can go ahead and try to determine the n hat dA over here. Now because we already have a surface is z equal to this. So surface is this type of surface, as explicit surface. Okay, yeah. So the n hat dA, okay, and then I can write it down directly, okay, as this. Okay. There. So you calculate partial f with x, partial f with y, okay, from here. Okay. What you're gonna here is you're gonna get negative 1 over 2. Okay. Negative is from the negative sign. Partial f of that is 2x, okay, over square root x squared plus y squared. Okay. And this one you get here 2y over squared plus y squared and 1 dx dy. Okay. Okay, so now I got n hat dA, and I can calculate the middle one there, okay, which is del cross f. So del cross f, okay, use the determinant thing, okay, I hat, g hat, k hat, okay, and the del, okay, f, you're gonna get is negative 4 I hat, negative 2x, g hat, plus k hat. Okay. Okay, so now you're ready to fill in the blank, right? Okay, fill in the blank over there. Okay. So what you get is you're gonna get this guy here. Okay. There. So this big one. Okay. So if you want to use Cartesian coordinates to do it, and it's fine, but there's a better way of doing it, because this is to determine x and y, right? The limits for x, y. The shadow of this cone, or the surface, okay, the shadow of this one in the xy plane is a circle. So you might want to consider to use polar coordinates. Okay, so use polar coordinates. That would be much easier. Okay, so if you use polar coordinates, you end up with a double integral, and the inside is 4 cosine theta 2r sine 2 theta plus 1, okay, and r dr d theta. Okay, make sure you get this stage. So the range for r and theta is determined by the shadow. Okay, it's 0 to 2 pi, okay, 0 to 1, and it's very straightforward. Okay, and you calculate that, and it should be okay, and you get 4 pi. There. So that's the hints for all the questions. The last question is also part of a tutorial for this week. Okay, so let me know if you have any questions, and I'll be happy to answer your question. Thank you. Bye.